Today, today we will discuss the chapter 8, the process quality. After completing this chapter, you should be able to do the following. First is to distinguish between common and assignable causes of variation. Second, understand the theoretical foundation for statistical process control. Third, identify implementation consideration for statistical process control. Fourth, create and interpret statistical process control charts. Lastly is evaluate a process's capability to meet specifications. The theoretical foundation. The fact that the normal distribution lies at the heart of statistical process control is truly fortunate or SPC. The mean and standard deviation are the only two parameters that can be used to determine every section of the continuous curve. Yes, the probability densities have been calculated according to a complicated function. So although those have already been completed by someone, but those calculations have already been done and tabulated, so we don't have to worry about them. The characteristics of the normal distribution. Any variable that we describe as normally distributed follows the same pattern. The mean determines how tall the curve gets, and the standard deviation tells us how spread out it is. Then no matter what normally distributed variable we are evaluating, we always know that one standard deviation or 1 or above and below, the mean represents 68% of all the possible values for the variable. Plus or minus 2 standard deviation is 95% and plus or minus 3 covers 99.7% of the possibilities as shown in the figure 8.1. So, it doesn't matter what the mean or the standard deviation is, this is probability density function will always be the same. So this is the graph of the normal distribution. So this is true whether you are comparing human characteristics such as man's height and standardized test results, or measuring other phenomena such as laser light density. Better yet, the normal distribution is often used to approximate other types of distributions because of the applicability of the central limit theorem, or CLT. Best of all, we can use the normal distribution to determine if a process is out of control by taking samples, calculating sample statistics, and plotting them in chronological order. If the distribution of the sample statistics does not change over time, the process is considered to be in a state of statistical control 1. So the common versus assignable causes of variability. We want to know if a process is out of control, so we will know when we need to make adjustments. All processes have variability. Think about styling your hair on a steamy July day in Georgia and then a chilly November day in Denver. Same hair care products, same comb and brush. In this case, it is environmental factors like humidity level, temperature, and altitude that create the variability. Common causes, also known as natural causes, are the purely random, identifiable sources of variation that are unavoidable in a specific process. In addition to environmental factors, there may be machine limitations or vibrations, such as human factors that are inherent in the process. A process is robust if it is susceptible to common causes of variation over the long term. You may be able to reduce this amount of variability with fundamental changes to the process or the new equipment, materials, technologies, and so on. In the short term, however, process adjustments are not warranted for common causes and can be actually make the variability worse. Assignable causes, sometimes referred to as a specific causes, include any factors that can be identified and eliminated. As stated in the opening quotation from the father of statistical process control, Walter H. shoe heart, toe wear, training concerns, and raw materials issues are all examples of assignable causes. The six major sources of process variation are: 1. People. 2. Machines. 3. Materials. 4. Methods. 5. Measurement. And 6 is the environment. The variations may be in terms of spread, the dispersion of the measurements or amount, the central tendency. This is illustrated in the figure 8-2. So you can see in the first schematic that the two distributions are the same in width and height but are concentrated in different points, indicating a shift in central tendency, the mean. In the second schematic, the two distributions are centered at the same mean, but the height and width of the normal curves vary because of differences in variation or the standard deviation. When assignable causes are present, process adjustment may be warranted. The action to be taken is situated dependent. Considering the cost of adjustment and the risk of poor quality, in some cases, a production line will be stopped immediately to investigate and ensure that no further assignable variation occurs. In other cases, the action might simply to take more measurements and then decide what to do. So this is the illustration of the changes in normal distribution in figure 8-2. So this is the shift in central tendency, then shifts in variability detected by our chart. So you might ask, how can I tell if assignable causes are present? The answer is that the normal distribution tells you: first, you establish what variability you expect under normal circumstances in the pond intended and create a process control chart. Then if you take a sample and the sample statistics are improbable according to all you know about the normal distribution, then you likely have an assignable cause. The following sections explains how to create control charts and interpret them to determine whether assignable causes are present. So, the control charts. To understand how assignable causes are identified, it is helpful to understand what a process control chart looks like. An example is shown in 8-3. In the figure 8-3, look at it is at turning the normal distribution in its side to create the y-axis. The x-axis is simply time. The dashed lines indicate standard deviation intervals above and below the mean, with the center line representing the mean of the distribution. Samples are taken and plotted in chronological order. So this is the illustration of the sample control chart in figure 8-3. The time, the period, the date, time, and the period, and this is the example. So to identify an improbable point based on what we know about the normal distribution, there are some simple rules of thumb. One point outside the three standard deviations on either side of the center line, because we know the probability of this is 100%, or the 99.7%, or 0.003. Three chances in a thousand. These limits are designated as the upper control limit or the UCL and lower control limit or LCL in figure 8-3. Two successive points between the second and third deviation on the same side of the center line. This is half the difference between 99.7% and 95.5% squared, or 0.0004. Seven successive points that are all above or below the mean, each one has a probability of 50%. Taken successively, the probability of 7 occurring in a row is 0.57, which is about 0.007. Another thing to keep in mind is the rule of 5, which says the 5 successively increasing or decreasing points looks like a trend and signals a process shift. There are many variations to these rules, all of which are intended to identify improbable occurrences, but some of which have complex underlying calculations. Attributes versus variables. So control charts come in a range of shape and sizes, and their sustainability is determined by what is being measured and the calculated statistics. Consider if you're working with qualitative or quantitative data when deciding which chart type to utilize. This can be perplexing at first because in both cases, you're using numbers in certain circumstances. Qualitative data has numerical values such n. A wide variety of control charts are used, and their appropriateness is based on what is being measured and the calculated statistics. One way to determine what chart type to use is to consider whether you are using qualitative or quantitative data. This can be a little confusing at first because in both cases you are using numbers. Numerical values of qualitative data are things like numbers of defects or count or fraction defective or percentage. They are used when you measure attributes, quality characteristics that have discrete values such as defective versus not defective. In this case, in these cases, you generally use attribute charts such as C charts based on the count of flaws in the sample, or P charts based on the percentage of defective items in sample. So quantitative data are tracked as variables, measures that are continuous and use rational numbers. Rational numbers are those for which ratios are valid. For example, a 4.4 foot board is 2 by 1 longer than a 2.2 foot board. Examples are thickness, length, width, and so on. When you are controlling by or for variables, you must use both charts. Why? Refer back to figure 8-2. You need the X chart to determine if there has been a shift in central tendency. The R chart alerts you to changes in the spread. Rangers are used in law of standard deviations to measure the spread as an approximation that is much easier to calculate when collecting the data. Chart mechanics. How best to get started with statistical process control seems like the chicken and egg conundrum. Which came first? How can you construct a control chart if you don't know whether your process is under control? Ideally, the central line and the control limits should be developed using data that were collected during a period when you believe the process was in control. Technically, though, you cannot determine whether the process is in control until after you have constructed a control chart. So practically speaking, when a control chart is first constructed, the center line and control limits are treated as temporary limits or trial values. So in the experiences, you start with 30 or more samples, calculate the sample statistics that you are charting, establish the control limits based on those statistics, and then plot the values of the statistics. If you do not detect any statistical improbabilities in these 30 points, you may consider the limits usable. If you do find that some parts of this sample violates our rules of thumb, you should investigate for special causes, correct them, and then measure again. When developing a control chart, you have 3 decisions to make. First, what quality characteristics of interest do you want to measure? Second, what is your sampling plan? Third, how much error are you willing to risk in your control evaluation? The quality characteristics you will measure is an important choice because measuring output has associated cost. The time to measure, chart, and analyze, and in some cases, the cost of waste if the product cannot be used after the sample is taken. The cost of waste if the product cannot be used after the sample is taken. So, measurables should be taken where the cost of poor quality is the greatest before a bottleneck because you do not want to waste bottleneck resources processing things that are low quality. Before a step that would obscure important quality characteristics. For example, once you sell once you sell a box or paint on the finish, it might be hard to detect underlying flaws before an expensive or hard to correct process is performed for reasons similar to those with the bottleneck. So this is the table 8.1, the control chart calculation. This is the chart, the line, the UCL, and the LCL. So with these decisions made, the construction of the control chart is quite simple. First, take 30 or more n or samples of size n. Second, calculate the sample statistics to be used in the control chart. Third, set the center line at the mean of the n sample statistics. Fourth, estimate the standard deviation of the process. How you estimate will vary depending on which chart you use, as shown in